Hey guys, in this video I'm going to show you a theorem called Stein Weierstrass theorem, or it has another name which I think it's more like up to point because it tells you what's the theorem about. It's called Weierstrass approximation theorem, so it's about approximation. And remember with the Fourier series and what is it called? Taylor series, yeah, Taylor series. There are some series that are trying to approximate some certain functions, but the functions have to meet some requirements, right? And Weierstrass is pretty much the same. So Weierstrass is trying to approximate a continuous function by a sequence of polynomials, or it's just use polynomials to approximate the functions. And in this video, or maybe I'll separate it into two parts, I will show you two ways of proving the Weierstrass approximation theorem. And the first one will be more elementary, and the second one we will utilize the help of dilated Gaussian kernel. Okay, so let's first see what's the theorem is like. Okay, the theorem is called Weierstrass approximation theorem. So it says given any function f continuous on AB, there exists a sequence of polynomials Pn converging uniformly to the function f on AB. So in other words, the polynomial that the sequence of functions, the polynomial that the sequence of polynomials converge to is the approximation of the function f, right? So you can also say there exists a polynomial that there is a polynomial that approximates to the function f. So how are we going to prove that? To prove there exists such kind of sequence of polynomials, we are trying to construct such kind of sequence of polynomials, right? So how are we going to construct this sequence? We will need some help. We will first construct another kind of functions and utilize it to finally construct the sequence that we want. And in the second proof, I will actually explain. It's actually not my explanation, but only my understanding of why people construct it like this way. Okay. So now, firstly, without okay, let's state proof. First of all, we do some little preparation. Without loss of generality, we assume two results. First, AB is 0 to 1. You can distort the domain of the functions or something to make it satisfy AB is equal to 1 and f0 equals to f1 equals to 0. Equals to 1. Okay. This should be 1. Yeah, I'm sorry. I think it should be 0. Sorry. f0 equals f1 equal to 0. And okay, and another thing is we f is let's let f be 0 everywhere outside outside 0 to 1. The reason we did this assumption is to make sure that f is uniformly continuous on R. Okay, uniformly continuous. So now what we are going to do, we are trying to approximate f, right? So in fact, the problem now transformed into we want to create an approximation of the identity. So we want to create an approximation of identity. Why we did that? What is the approximation of identity? So I didn't mention in the previous video or in any other videos because we haven't got there, but the approximation of the identity is actually the approximation of so what is identity? Identity is simply delta function, direct delta function. So because delta function has a certain property that if you take the convolution of the delta function of any other functions, you will get exactly the value of that function at any point. Since some functions are quite complicated, but with the direct delta function, we can easily get its value. So their function is something called the identity, and now we are trying to approximate a polynomial to the function f. So we are trying to actually approximate the polynomial to the identity, right? So we are trying to create approximation of the identity. So that's what we call it, approximation of the identity. Okay. Also, we create another function q, and actually it's a sequence of functions. I think. Let qn be cn times 1 minus x squared to the power of n, and which is on minus 1 to 1. And also here cn is, where cn is actually 1 over the integral of 1 minus x squared to power n dx on minus 1 to 1. Okay. When we did that, you will see actually we if we observe the functions that we just create, you will find that actually if we take the integral from minus 1 to 1 of qn, you will get the integral is equal to 1, right? Because, well, cn is just a value, a number, right? It's a value, because you are taking the integral of it from minus 1 to 1, right? Well, it has n, but it's it's I'm sorry, it's not a value. It's not a value, but it's you are integrate it with respect to x, so x will disappear, right? And you will there will be only n left. And since we are take the integral of qn, and you will see that actually you can move the cn outside the integral, right? And the rest of it is the inverse of cn. Okay, so actually it's the integral of qn with respect to x on minus 1 to 1 is equal to 1. Okay, The second observation is that you will find for any data lie in 0 to 1, interval 0 to 1, Qn converge to 0 uniformly on x less than delta, x larger than delta less than 1. So if we draw a graph like this, here minus delta, and here's 1, minus 1 and 1. So the function is defined between minus 1 and 1. But you will find that when x is in this part, the function is getting smaller and smaller. It is closer and closer, getting closer and closer to 0. And in between delta, minus delta to delta, it pops up. It spikes. It spikes so that you will get the interval. The integral of it will be 1, right? Because, well, you can actually take delta to be very small, extremely small, but no matter how small it is, the function will spike near 0, near the origin, because it has to, because its integral has to be 1, right? And up to now, you can already see that we are like trying to approximate delta function, because what's delta function? Delta function also have the property that delta function is also that like the delta function is 0. Delta function is 0 almost everywhere, except for the origin 0. So and also its integral over the real line. So suppose delta x. So delta x is 0 almost everywhere, except for origin point. And if you take the integral of it, it will be 1. So it will like spike near the origin, because it has to be, because the area of the function will be like circumscribed by the function, and the and x equals to 0 will y equals to 0. The area of it will be 1, because it's the meaning of the integral, right? And it's 0 other than the point, it's 0 other than at the point x equals to 0. So you will probably see that these two kind of function are pretty much similar. We do try to like approximate it to delta function, right? Also, we will see. Okay. It's quite simple to say that Cn that we create there, Cn is smaller than the square root of n. How are we going to show that? I'll leave it to you. You can just prove it by mathematical induction. It's quite simple. Cn is less than the square root of n. Okay, so with this property, we will now say that Qnx is less than, well, Qnx is equal to Cn times the term afterwards, so it's less than square root of n times 1 minus x squared to the power 1, right? And we also know that in the interval, when x lie in this interval, the absolute value of x is less than delta and 1, you will get 1 minus x squared is less than 1 minus delta squared, right? This is pretty simple, right? So what we're gonna get after this inequality, we will also get qn smaller than the square root of n times 1 minus x, 1 minus delta squared to the power n, right? Okay, so what we get now, we also know that the limit of the term will be 0, right? If you let n tends to infinity, because this part will be extremely small, and if you take the n's power of it will be getting smaller and smaller, and the speed of it tending to 0 will be much faster than square root of n. So the whole term will be tending to 0. Okay. So, well, here I'm just explaining the observation we just got, right? Qn is uniformly converging to 0, right? And as x lies in the small interval, the absolute value of x larger than delta and less than 1. Okay. So next part. Okay, we haven't get to the point of really constructing the polynomials, but now we are gonna define the polynomial. So the sequence of polynomials. So how we can define that? We define Pn x has. Okay, so this is the sequence of polynomial we wanna prove. We wanna construct. Pn x equal to the integral from -1 to -1 to 1 f(x) plus t times qnt dt. When I first saw the proof of this theorem, I didn't understand. I didn't see why he did that. Why people construct Pn this way. But after I see the second proof afterwards, I actually see it in the book. Who talking about Fourier analysis. So this the reason people construct it this way is to approximate it as a convolution of fx, and the identity we just construct, right? Okay. So the thing is, when you define Pn, when you define the sequence of polynomials, you are utilizing the function itself, f, and what is the kernel, and the approximation you just construct. Okay, so this is how you define the sequence of polynomials. Well, I'm saying that it's a polynomial, but in fact we have to prove that it's a polynomial. It's a polynomial because from the way you construct it, you can't tell it's a polynomial, right? So we need some little more step to prove it's a polynomial, but it's very, very simple. So first of all, Okay, now we are claiming two things. First is that the Pn x we just create is polynomials. Pn is a polynomials. Polynomials. Okay. And second thing is Pn actually converge uniformly to f on 0 to 1, right? Because if we can prove it's because it's actually what's the theorem said, right? We find the polynomials and prove that it's uniformly convergent to f. Okay. The first claim is very simple because, well, now Pn is what? Pnx is, you write it down and analyze it a little bit. You will get, here we change a little bit of a variable. You'll find what? You will find that, okay. Here we know that so here's a step of change of variable. Well, Qn, as we defined, is equal to Cn times 1 minus, now x is t minus x, so t minus x to t minus x squared to the power of n dt, right? Okay. Right. And it's clear that we get here some sort of polynomials, right? Because if you expand it, you will always have some certain polynomials with respect to t minus x, right? I'm sorry, with respect to x, because t will be because, well, the integral is you're taking the integral with respect to t, so t will disappear after the integral you're calculating, but x will remain. So x will be left. So the result will be some constant times will be the sum of some constant, if we call it an, times the t to the power of, well, n or something like that. Okay, so we prove that this Pn is a polynomial. Okay. I'm sorry, I didn't mention here. Here we got, well, we are taking the integral on minus 1 to 1, right? So we got x plus t will be larger than 0 and less than 1. So t will be larger than minus x to 1 minus x, right? So this is the reason why I write it this way, because I want to change a variable from x to t. Yeah, I want to change a variable to from x to t. To integral t and to integral with respect to t. Okay. So the second part is to prove that Pn converge to f uniformly. Okay, first of all, to prove its uniform convergence, we just using the definition of Cauchy criteria, right? Still, we fix a epsilon larger than 0, and we want to show there exists n such that when it's larger than n, we have Pnx minus fx. The difference of it will be less than epsilon, right? For any x lying 0 to 1. This is how we're gonna prove the uniform convergence. So here we got Pnx minus fx. The difference of these two terms will be, well, you first write down all you've got, and here there is a trick. It's a trick that you're playing with the number 1. So if you directly write it down to be Pn minus fx, there will be the first term will be integral, and second term will be only fx, right? But we wanna to take the function fx into that integral, so we somehow create the number 1. So we get that fx times the thing that we just proved, qnt is equal to, the integral of qnt is equal to 1, right? We prove that this integral is 1, and we put fx into that integral because it is integral with respect to t, so it doesn't matter if you put fx in it, right? So what we got x plus t minus fx times q and t, right? dt. Okay. And since fx is continuous, right? And it's actually uniformly continuous. We proved that it's uniformly continuous. We do some distortion to make it uniformly continuous on the real line. So we will get okay, here we also have to put the absolute sign into the integral. We will get, well, if we separate it into two parts. When t is less than delta, what we get? Okay. When t is less than delta and when t is larger than delta. And the separation of you separate an integral into two parts is also a trick that we will constantly use it. It's pretty simple, but it's quite useful, functional. Because sometimes functions have different properties on different interval. Sorry. Okay, so we can choose a delta because it's uniformly continuous, right? We choose a delta such that if the absolute value of t is less than delta, we have fx plus t minus ft. Minus fx will be less than epsilon over 2, right? In the beginning of the proof, we fixed epsilon, and now since it's uniformly continuous, we can find such delta, right? Such that the difference between fx plus t minus and fx is less than half of the epsilon. So what we get? So we continue doing the equation here. It will be like smaller than half of the epsilon times the integral of q and t dt plus right? We are about to finish it. What else do we know? We know actually f is bounded, right? F is bounded on 0 to 1 by some m, right? Okay. F is bounded. In fact, so last thing is, well, since it's bounded, we will have the inequality will be plus 2m. Well, since f is bounded, the absolute value of this of the difference will be smaller than 2m, right? Times so this term will be smaller than 1, right? Oh, sorry. This yeah, actually it's true. Well, previously I'm like integral take the integral of qn on the small interval smaller than -1 to 1, but if we extend it to -1 to 1, it will be getting larger. So and this term is equal to 1, right? So what we will get times 1, half of the epsilon times 1 plus 2m times epsilon over 4m, which is equal to epsilon. Okay. Have we got that? Have we got qn, if we take the integral of qn on the small interval is epsilon over 4m? Well, we can't do that because what did we get? Because qn is, well, in that interval, because qn is tending to 0 uniformly, right, on this small interval, right? So we can have such thing. Okay, so we prove that Pnx is uniformly convergent to fx, right? Okay. Okay, so we're done. We proved that there exists a polynomial Pn of the form fx plus t times q and t dt, and take the integral of the term from -1 to 1. Okay, so such kind of a sequence of polynomials will converge uniformly to the function fx. Okay, So this is the first part of the video. I've shown shown the proof of the theorem. The first proof of the theorem. Okay, and we also have I will also show you a next one.